Hey everyone, this is Dr. Walker and this is video 86 on traveling waves. What do you think about when you think of waves? Do you think about ocean waves? Well, those are definitely a type of wave, but there are so many waves. What about radio waves or ultrasound waves or sound waves from musical instruments? All of these waves are called traveling waves. Traveling waves are periodic disturbances traveling through a medium. Periodic means it's going to occur over and over again. The medium is the substance through which the wave is moving. Let's consider the dominoes here. They're falling down. As they're falling down, you can see a pulse that is moving through the dominoes. So it's just a pulse because it's not periodic, right? They're just falling once. So you see that pulse or that disturbance traveling through the medium. The medium is the dominoes. The dominoes themselves are just moving downward, right? This domino is not moving all the way over here. The wave is moving through the dominoes, but the dominoes themselves here are just moving downward. Think about dropping a pebble in a pond. The wave is these ripples here that you see moving outwards. The medium is the water. The water molecules themselves are just moving up and down in this case. All waves carry energy. As these dominoes fall down, the medium, or the elements of the medium, which is in this case the dominoes themselves, they transfer their energy to the neighboring dominoes. And that's how you see the wave propagating as the energy is being transferred and is propagating. Let's go ahead and describe waves. There are two types of waves. Transverse waves is where each element moves perpendicular to the wave motion. In this case, somebody flicks their wrist and we see the pulse traveling along the string. So the medium is the string. The wave or the pulse is moving along the string. But the string elements themselves are just moving up and down. Right? This part of the string is not moving all the way to here. It's just moving up and down, and that allows the wave itself to travel. Another good example of a transverse wave is light, which we will discuss in Physics 2. The other type of wave is a longitudinal wave. In this type of wave, each element of the medium is moving parallel to the wave motion. Think about a slinky. If you compress it and stretch it, you will see that pulse moving through the slinky. But the elements of the medium themselves, of this metal slinky here, they're just moving left and right. But then you will see the pulse traveling through the whole slinky. A great example of a longitudinal wave is a sound wave, which we will be talking about in this chapter. Now let's go ahead and describe the properties of the wave. This is going to look very similar to what we did when we talked about simple harmonic motion. Just keep in mind that simple harmonic motion is different. Remember when we were talking about that spring? And that spring was moving, that you had a mass on a spring, and it was moving different positions from equilibrium, right? It was being stretched and then compressed. And we said the motion of the spring was sinusoidal, but the spring itself was just oscillating back and forth. That was simple harmonic motion. What we're looking at in this chapter is traveling waves. So you'll have a wave and it will have a sinusoidal nature. If the source of the wave is oscillating in simple harmonic motion, it will create this type of sinusoidal traveling wave. But what we want to focus is that the wave itself is traveling. So that's why I have this big arrow with a velocity here, right? So imagine this whole wave traveling. Instead of what we were imagining with simple harmonic motion, we were imagining our object that was moving up and down. So the amplitude is still going to be the maximum displacement from the equilibrium position. So just as before, and it's going to be a distance, so it's going to be measured in meters. The wavelength is a distance spanned by one cycle of motion. So distance from one crest to one crest, or a trough is the lowest point here. If you had another trough here, right, this would be the wavelength. In this case, you can imagine the wave that is traveling, and you can imagine that this crest moves all the way to here. And so it spans a distance of a wavelength, which is a distance, so it's still measured in meters. Next thing is the period, the time for one complete cycle. So instead of thinking about, again, a mass oscillating and how long it takes to do one complete cycle, think about a point on the wave that is traveling and how long it takes to get to this location. As this continuous wave is traveling, right, this point is going to get here. How long does that take? That's going to be the period. Period is measurement of time, so it is measured in seconds. It can be a point on a crest moving all the way to that same position, or it can be any point on the wave as long as it moves through a whole cycle of the wave. Just as before, the frequency is going to be the number of cycles per second, which is going to be defined as 1 over the period, and the unit is in hertz, which is also 1 over a second. Now, I do want to go back. I did forget to mention something. Let's make sure that we consider what kind of graphs we were looking at. For amplitude, we were looking at a graph of y versus x. We were looking at distances on both axes. We were also looking at distances on both axes when we were looking at wavelength. But notice that the graph did change once we got to period. We were now looking at a distance on the y-axis, but a time on the x-axis. So really be aware of what is being graphed, because otherwise you might be looking at this and you might be thinking, oh, I thought that I just said that was a wavelength. But because we're looking at time, that's why now this is defined as the period. We don't really have a good graph for frequency, so I just use the same graph as the period, but you could think about if you have 1 second, let's say that 1 second was right here, right? Then you would say, okay, there's 1 cycle, 2 cycles in that 1 second. That will be the frequency, 2 cycles per second, or 2 hertz. And the last thing is the speed of a wave. So this picture is emphasizing that the wave is traveling. So we have the red wave is the original wave, and then it's moving to the position where now you see the blue wave. So how far has it traveled? Well, it has traveled a distance of the speed times the time. But if we considered that it has traveled a distance of the wavelength, so let's say it went from here all the way to here, then how long would it take to travel that distance of a wavelength? Well, it would take a period to travel a distance of a wavelength, because the wavelength is the full cycle. So if you use wavelength over period as your distance over time, then you can see that the expression for the speed of a wave simplifies to wavelength times frequency, because frequency is 1 over period. The speed of a wave will be measured in meters per second. Let's take a look at one question. What is the period of this wave shown? Well, we're given that it travels at a speed of 1 meters per second. So we're given v. And to find a period, then we know that the speed is the wavelength over the period. So the period is going to be the wavelength over the speed. So we need to figure out what is the wavelength. Well, let's look at what this graph is showing. It's showing a distance. This d is the same thing as y here. It's a distance and a distance. So we know that the distance between successive crests is our wavelength. So our wavelength is 2 meters according to this picture. So it's going to be 2 over 1. Our period is going to be 2 seconds. We're going to keep describing waves in the next video.